Welcome to this webinar on HDR, basics of HDR. I hope you can all see me and hear me. Now today we have me, Paul Cameron, and Gisbert. Gisbert is joining from Cologne, and Gisbert is my partner in this presentation, and he's going to be in the background fielding all of your questions. Gisbert, are you there?
Yeah, I'm here. Thank you. And welcome to this webinar today. I hope you will enjoy it. And it is Paul who will make the presentation, and I will try to answer your questions in the background if there are any.
Great, thanks, Gisbert. With regard to the questions, if you have a look at your GoToWebinar control panel, you should see a small area there where you can type in questions. And Gisbert will be tracking those questions and try to answer the questions as much as he possibly can in the time that we have. Now, when I finished this particular presentation, Gisbert will rejoin and we'll all discuss the questions that have come through and hopefully get through as many questions as we can before we run out of time. We do have to go home this evening, so please try to keep it fairly brief and short. Feedback as well. At the end of the presentation, it'd be nice to have some feedback from all of you as to whether you liked or disliked this presentation. So give us feedback when we finish this presentation. What are we going to talk about today? Well, we're going to talk about the business benefits of producing an HDR, what the business benefits of high dynamic range are. I'll go through some of the concepts and the terminology. We'll look at the basics of HDR, what it is and how our eyes work and how sensors work and so on. We'll take a look at some of the industry standards and the specifications behind high dynamic range. And we'll look at some of the operational practices and workflows for high dynamic range. And finally, look at the products that we have to support high dynamic range workflows. So what are the benefits of HDR? Well, benefits today, more impact, making images stand out in a crowded market. It's a way of making presentations and programs stand out against all of the other paraphernalia that's being shoved out there all the time. It really puts the viewer at the heart of the action. High dynamic range makes you feel as though you're involved as a viewer in the images that you can see. From the broadcaster's point of view, they can upsell HDR services to any of their standard dynamic range subscribers. Production companies and freelancers can also use high dynamic range to win new business for their high value projects. I need to move the controller to the side because I can't see the top of the screen. Benefits tomorrow. HDR programs are ready for new distribution opportunities in the future. So anybody producing HDR programs can then use this to open up new distribution opportunities. Archived HDR content can be repurposed. So even though a lot of the customers might not be viewing in high dynamic range at the moment, the archive is in high dynamic range and it provides opportunities for the future. It also means that high dynamic range content can be sold in the future to third-party programs. So let's go right back to the beginning, have a look at HDR concepts and terminology. What is HDR? What is high dynamic range? Or more to the point, what is dynamic range? Well, dynamic range is all about the brightness in a scene, an image, display, or a picture, from the darkest objects of the scene to the brightest objects. So a scene like this, for instance, has a fairly narrow dynamic range. A foggy scene like this, there isn't an awful lot of difference between the darkest areas of the picture and the brightest areas. Scenes like this are quite easy to capture on pretty much any camera. It doesn't present an awful lot of a challenge for the production workflow. However, images like this are high dynamic range, and you can see in this image, this dark area here has been beautifully captured, but at the expense of the sky here. And it shows really what a challenge high dynamic range can present to anybody producing programs. In this particular case, the sky's burnt out. So you do need to have high dynamic range equipment right the way through the whole workflow, all the way from the camera through the production system and out into people's homes and out onto the screen, or indeed in the cinema. So let's go back to the basics. Let's have a look at the way the human eye works. Now, we all know this. The human eye picks up visible light over a very narrow spectrum of electromagnetic spectrum, from infrared all the way through to ultraviolet. These are all of the colors that we can see in nature. Early experiments with the sensitivity of the human eye gave diagrams like this, and this is a diagram that came out of the experiments back in 1931, trying to find out what the sensitivity of the human eye was to brightness and to individual colors, in particular red, green, and blue. And this gave us this concept of red, green, and blue primaries, as you can see here. And we selected certain wavelengths as the primaries for red, green, and blue. And that eventually gave us what we call the CIE color space. Now, we're not really talking about color in this presentation, but I think it's quite useful to see where this color space came from. Now, you've all played around with color selectors like this in Photoshop or Photo Paint or any color selector that you've got on your computer. And these color selectors allow you to select red, green, and blue. You can see here, here, down here, anywhere between 0 and 255. So you can kind of imagine that you can present or represent these colors as 3 axes, red, green, and blue. And if we fill these axes in, we can build a cube. And that cube has black in the bottom corner, you can see just here, going all the way around to white in the top corner, with magenta in this corner, blue here, green here. You mix blue and green together, you get cyan. If I turn this cube round the other side, you can see the back of this cube, and you can see the red axis going along the back here. You mix red and green together, you get yellow. There's magenta in the bottom corner and white up here. So let's turn the cube back round again. Now what I'm going to do is to slice this cube right down the center. And what that reveals is a line that goes all the way from the black corner all the way up to the white corner at the top. Now that's a line of brightness only, and this is where it gets interesting from a dynamic range point of view. This line is representing brightness only, from the darkest areas to the brightest areas. So let's close the cube up again. And now what I'm going to do is to turn this cube round slightly and make it a little bit transparent so that we can see through it. And you can see that brightness line going from the black corner at the back to the white corner at the front. Now I'm going to use a little bit of mathematics. Don't worry, the mathematics doesn't get any more complicated than this. And reverting back to the diagram that I showed you earlier from the early experiments back in 1931 of the sensitivity of the human eye. And if I use this mathematics here to plot the maximum saturated colors all the way from blue right through green through to red, this gives us this strange horseshoe shape inside this cube. Now, human vision has a limit at ultraviolet and infrared, which gives us a limit of human vision, which we can draw as a line across the bottom of this shape. So there you have it. There's the beginnings of the CIE color space. Now, if I bring the cube up straight, so we're looking straight down the brightness line, you can see that this shape has this characteristic horseshoe shape. If I turn the cube round, you can also see that the brightness line is perpendicular to the color. The color plane, showing all of our sensitivities to color, is perpendicular to the brightness line. Let's bring it up straight. There we are. And what we can also do is to add some dimensions, some coordinates to this diagram, and it's starting to look like the CIE color space. This is where it gets interesting from a dynamic range point of view. If I turn the cube sideways like this, we can now show the brightness vertically. That's the dynamic range, and the color horizontally. And it also allows us to fill in the overall volume of the extremes of human vision, going all the way from white at the top to black at the bottom. And anybody who has played around with something like Photoshop or anything like that, you know that if you take a fully saturated color and you increase its brightness, then eventually it loses its color saturation and goes to a pure white. And likewise, if you decrease its brightness, it loses its color saturation and turns black. So that's the basis of the CIE color space. But just remember that this CIE color space is actually a volume of sensitivity for the human eye. It's as if you're looking from the top of this volume and it stretches all the way down into the screen. Now, the sensitivity of the human eye is basically logarithmic, and the dynamic range can be represented by this line here. We have more dynamic range or more latitude at the bottom than we do at the top. In other words, we tend to see more detail in the midtones and the shadow areas of a picture than we do in the highlights. If you're outside looking at the sky, you tend to see the clouds crushed. The detail in the clouds tends to be crushed. We tend to see more detail in the shadows. It's interesting to note also that what we regard as 50% brightness is actually sitting at 18% grey. And photographers and cinematographers often use a grey card like this Kodak grey card here, an 18% grey card, to match cameras and set cameras up. This card is actually sitting at 18%, even though the human eye sees it at about halfway between black and white. Now, the human eye has a sensitivity, a dynamic range of about 10 to 14 stops. Nature, in all its cruelty, presents us with 24 stops of dynamic range. Now, I'll talk about stops later on, but it's interesting to note that the irises in our eyes allow us to see all of this 24 stops of dynamic range by opening and closing as we move from one scene to another to allow us to see as much detail as we can in the world around us. Now let's compare that to the image sensor. Image sensors in modern cameras can give us at least 14 stops of dynamic range. So they perfectly match the capability of the human eye. You can see here a live production camera on the left and a cinematography camera on the right. The sensors in these cameras have the same sort of capability, probably a little bit more than what we have in our own eyes. Image sensors are designed to be linear. And from the darkest areas, you can see in this fireplace here, where the picture disappears into the noise, all the way up to the brightest areas, the window here, where the sensor saturates, it's a straight line between those two extremes. Sensors are designed in this way. Now that's in contrast to the way the human eye works. However, when we look at the dynamic range of sensors these days, about 14 stops of dynamic range, in much the same way as we do with the human eye, we can open and close the iris to capture as much dynamic range and as much detail in each of the scenes we are shooting in much the same way as we do with the human eye. So measuring light and dynamic range. One of the most common ways of measuring brightness in a scene, certainly when we're talking about dynamic range, is the nit. Now there are several ways of measuring light, but the nit is probably the most popular when we're talking about dynamic range. Sunlight gives us billions of nits of brightness. Up here you can see. Computers nowadays, at least 200 nits. Mobile phones the same, maybe 400 nits. Anything below a nit is generally regarded as a shadow. Lighting anywhere between 15 and 5,000 nits. So mood lighting in a restaurant, maybe 20, 30 nits. But on a showroom or an exhibition hall, then the brightness might go up into the thousands of nits. It's interesting to note that high definition television, this is the Rec. 709 standard, in 8-bit form, which is the way that we normally transmit television in high definition, will achieve just 100 nits. So even though home televisions are capable of going beyond 100 nits, the standards themselves do not allow much more than 100 nits. Now this is useful when we're talking about high dynamic range, because 100% of high definition television neatly is 100 nits. So 100% equals 100 nits. Now I talked about stops. What is a stop? Well, anybody who used a camera will know perfectly well what a stop is. There are standard stop values, f1.4, f2, f2.8, and so on. And as you go up in these values here, it's halving the area that the light can get through. In other words, it's halving the amount of light that can get into the camera. If you go up, it's doubling the amount of light. So each stop up and down is halving or doubling the amount of light that goes into the camera. Now you can measure the dynamic range of a camera very easily. Point your camera at a white card, set a reasonable ISO and setting and a shutter setting to make sure the picture is nice and bright and white. Now you do need to have a lens with a nice big aperture, the biggest aperture possible, really good idea. Take a few shots with different apertures. You decrease the aperture by 1 stop each time. What you end up with is a bunch of pictures like this. So organize the shots, take out all of the white shots except for the last white shot. Then take out all of the black shots except for the first black shot here, and the dynamic range of that particular camera is the number of steps between white and black. In this case, 1, 2, 3, 4, 5, 6, 7. 7 stops of dynamic range in this particular camera. The better the camera, the more gray pictures you will have between black and white. Now you can do the same thing with the video camera. You need to set a low ISO, set the gain to 0, and shoot a number of clips, and you can do the same thing. Now in displays, we normally measure contrast ratio, not dynamic range. There are 2 types of contrast ratio: static contrast ratio, where we look at the contrast ratio in one frame, one picture, and dynamic contrast ratio, where we measure the brightness between 2 frames. Whichever you choose, the measurement comes out in a similar way. We measure a white area and a black area. On a photometer, we divide one from the other, and it gives us the contrast ratio. So that introduces a question. What is the comparison between contrast ratio and dynamic range? Well, this table here shows us the comparison between contrast ratio and dynamic range. And it's interesting to note that with 8-bit Rec. 709 high definition television, we're sitting right up here. This is the reason why we're moving towards high dynamic range. We're getting barely 100:1 contrast ratio, barely 6 stops of dynamic range in Rec. 709. Human vision, as I said earlier, anywhere between 10, 14 stops, something like that. Modern technology, we can now achieve anything up to about 16 stops, and we have monitors, certainly professional monitors, that can achieve nearly 1,000,000:1 contrast ratio. So that's where we are at the moment, and this is why we're trying to introduce new standards to move beyond Rec. 709 into new territory where we can start to take advantage of these extended dynamic range areas. Now, looking a little bit more at high definition television, 1920 by 1080, most transmissions are interlaced, but you can have progressive as well. This is what Blu-ray supports. It's the first format that's supported by Blu-ray. There's the Rec. 709 color space, quite restrictive by today's terms. And here is the overall volume. So by taking this CIE color space diagram, flattening it down, and then showing the dynamic range in the vertical direction, we can see the overall volume that we can see in high definition, going up to right at 100 nits. Turning our attention to 4K and Ultra HD. Ultra HD, 3840 by 2160, 4 times the resolution of high definition. This is the form of 4K that has been selected for general broadcast, for sports, for live production, for consumer television. Now, when we went from standard definition to high definition, it was really only an increase in resolution. Every other aspect of the picture remained more or less the same, in particular, the color and the dynamic range. Now, designers realized, the AV media community realized that moving on to Ultra HD, we needed to present customers at home with a lot more than just an improvement in resolution. So there are 6 definable improvements in the picture quality for people watching television at home. Now, for us at the production end, we're not so interested in audio. This provides us with multi-layer, multi-dimensional audio for people watching television at home. But for us, we're really only looking at these 5 improvements. For the frame rate, it's simple. We're doing away with interlace. So Ultra HD is progressive only. This is a big improvement. For bit depth, we're moving from 8 bits to 10 bits. So all the images sent out to people's homes are now 10-bit quality. This gives us the ability to improve the color and improve the dynamic range. So bear in mind, the bit depth and the color are linked together. The bit depth and the dynamic range are also linked together, but color and dynamic range are 2 separate parameters. Remember the diagram that we had earlier on. There is another form of 4K, DCI 4K. Now, in Sony, we do have a number of products that support this, specifically for cinematography, with an aspect ratio of 4096 by 2160. And you'll notice that some Sony products have this 17:9 aspect ratio. Looking Ultra HD though, Ultra HD now supports a much bigger color space. So the color is much bigger. Looking at the dynamic range, that's also bigger, stretching all the way up to 10,000 nits. And one of the standards in particular goes all the way up to 10,000 nits. This increases the overall volume of color and brightness that we can now transmit using Ultra HD. So let's turn our attention back to high dynamic range. Sensors can produce at least 14 stops of dynamic range. The amount of data coming out of the sensor is extremely high. So we use a variety of gamma and log functions to squeeze this quality into a standard video signal without losing any of that wonderful dynamic range. You see, the problem with standard dynamic range is this. If I close the iris down in the camera, I can capture the brightness out here quite well, but I've lost detail in the shadows. If I open the iris, the detail in the window is burnt out, but I can now start to see detail in the shadows, and I hope you can all see that black cat. What we want is both. And of course I fake this up because my screen is standard dynamic range, but now you can see this window is nicely balanced and I can still see the cat in the shadows there, and I hope you can all see that. So that introduces the concept of transfer functions. The sensor produces a linear output like this, maybe 16 bits large, stretching in this case, and I've used just 1,000 nits to illustrate this dynamic range. We want to then transfer that into a standard 10-bit video signal. Now I could keep the video the same. That would burn out almost anything with any kind of brightness in the picture. It would just clip badly and all of the highlight detail would be lost. On the other hand, I could just flatten the whole lot. This would make the mid-tones and the lowlights very dark. So remember the characteristics of the human eye. What we're going to do instead is to introduce this curve that in some ways copies the way that the human eye works to retain a lot of the brightness down here in the lowlights and the mid-tones as we had coming out of the sensor. But then as we go brighter and brighter, it's squeezing to fit all of that dynamic range into the available space for that particular video signal with 10 bits quality. Now that's what we call an optoelectrical transfer function, or an OETF. This is the transfer function in the camera that is turning the signal from the sensor into some kind of standard video signal that we can send out. In the monitor at the other end, the display at the other end, we take this video signal and we apply it to a curve that goes the other way, and that produces a nice straight line that we can put out onto the screen. And this curve in the monitor or the display is the EOTF, the electro-optical transfer function. So here's the whole chain coming from the camera with its OETF and the display with its EOTF. And if we add the OETF and the EOTF together, we have the optical transfer function. And this is a description of the whole transfer function throughout the whole chain. In a perfect world, the EOTF and the OETF should be the opposite of each other, and the OOTF should be nothing. And we see on the screen exactly what the camera picked up in nature. But things aren't perfect, and you'll often find that the screen can't quite match the capabilities of what the camera is capturing. Just an example, for instance, let's imagine that this particular screen can't quite get up to 1,000 nits. Well, in this case, we're going to clip a little bit. So we have to change the EOTF, pull it down just a little bit to fit that picture onto the screen. So in this case, the OOTF would show the overall change from what's coming in the sensor and what's going out on the display. So what are the industry standards for high dynamic range? Well, there's a very important document, the ITUR BT 2100 standards document, and this specifies two transfer functions that we can use in the industry. The first one is hybrid log gamma, or HLG, and as it says in the document, it offers a degree of compatibility with legacy displays by more closely matching the previously established television transfer curves. In other words, it offers a degree of backwards compatibility. I'll talk about that a little bit more in a minute. Perceptual quantizer, or PQ, achieves a very wide range of brightness levels for a given bit depth using a non-linear transfer function that is finely tuned to match the human visual system. So this is seeking to tune the television to exactly what the human eye is going to see or can see. So looking at this whole chain here, from the sensor going through to the display, we can talk about scene referred and display referred transfer functions, looking at the OOTF. And you'll hear this mentioned in broadcast circles, the sort of transfer functions that we use overall. Some of them may be scene referred and some of them may be display referred. The scene referred transfer function basically is referring the overall transfer function to what is coming from the scene itself, the light that's coming from the scene itself. The display referred transfer function is actually referring to the display and seeking to give the display a particular brightness for people watching the screen. Looking at the BT2100 standard, this offers two chains. Now this is the PQ chain, and in the PQ chain, the standardization is at this end here. It's display referred. In other words, the data is seeking to prescribe a particular brightness on the display. Whereas hybrid log gamma, on the other hand, is a scene referred transfer function, and this is referring the overall data to what is coming from the original scene, the brightness of the light from the original scene. So here are the curves for BT709, and there it is, Rec 709, there it is, peaking at 100 nits. And you can see here hybrid log gamma stretching right out here, and PQ stretching out here. And I've neatly tucked into it a third curve, which I haven't mentioned. This is S-log. This is not an industry standard, but this is Sony's specific high dynamic range curve that we use in a lot of our products. And you can see how closely matched it is to HLG. I'll talk a little bit more about Sony's S-log in a moment, but just turning our attention to HLG, I did mention that it was backwards compatible. What does this mean? Well, Rec 709, here it is. It's following its standard Rec 709 gamma curve. Now, looking at hybrid log gamma, the first part of hybrid log gamma is the gamma portion, neatly copying Rec 709 in its gamma, but at a lower peaking level. Now that gives us enough space to then add on to it a log portion. And that gives us a total hybrid log gamma curve that is a combination or a hybrid of log and gamma put together. That's what makes it backwards compatible. The ITUR BT recommendations also specify either hybrid log gamma or PQ at a number of resolutions. So this actually allows us to send out high definition material, 1920 by 1080, using one of these high dynamic range curves. The color space is defined as 2020 color space. This is the new, really big color space that I talked about earlier. And you can send out in 10 bits or 12 bits for extra quality. Notice, no 8 bits there at all. So this is really pushing the quality. A variety of different frame rates. We've got standard frame rates and drop frame rates as well. And you notice at the bottom here, progressive only, no interlace. Turning our attention to S-log 3, just a mention of that. Now, S-log 3 is an OETF designed by Sony, and you'll find this in a number of Sony products. It's ideal for 10-bit production systems, and you'll find it in some of our cameras. It's an excellent production format when converting to both HLG or PQ. It's scene referred, so it's very similar in this respect to HLG. It's referring to the scene and the light coming in from the sensor, and it's used around the world by a number of film and documentary producers for their live productions. S-log, when you look at S-log material directly out of the camera, it looks kind of flat and unsaturated. However, we have managed to capture all of the color and all of the dynamic range in this picture. You can see, for instance, the bulb here in this lamp is still very clear, and the transition from red to green is nice and smooth. Now, we could send this into a grading suite and we could grade it, for instance, to Rec 709 if we wanted to. Something has to give. The colors are looking nice and bright now, but you can see the bulb is burnt out. And you can also see a hard clip in the green just here. Now we could grade this again. We could grade it for high dynamic range, maybe Ultra HD. And in this case, this light would probably be visible. You'd probably see the bulb and it would be a lot brighter. So that's the beauty of S-Log. It allows us to capture all of this dynamic range and then in post-production, turn it into whatever output we want. So let's have a look at HDR in the delivery chain. Now this is showing a standard Rec 709 distribution chain using a standard television. It's coming from the camera. It's already burnt out, it's clipped. You can see the dynamic range here gone in the production. And then we send out into people's homes, and this is the image that we get in people's homes. Badly clipped for dynamic range and quite a restrictive color space. Now, televisions at home are a lot brighter now. We can go beyond 100 nits, but that's not going to make an awful lot of difference because we're burnt out, in fact, back in the camera. So we need to start again. And in a modern high dynamic range, large color space production system, we would choose one of the log or gamma functions like HLG or S-Log3 if it's a Sony camera, with a wide color gamut that we can put into the camera when we set it up. Then we can come into production using these curves and these color spaces, and then transfer in post-production to one of the industry standard outputs for delivery into the home. The color space is transferred to 2020, and we can deliver out into the home and retain all of that wonderful dynamic range and color. And you can see the EOTF there in the television in people's homes. We also have something we call instant HDR. Some of our camcorders can transmit directly out on air. Maybe you want to do a web transfer or web link going out directly onto the internet. By setting the camera directly to HLG in a 2020 color space, we can effectively miss out the production cycle and go directly out on air. For live production, we have something called the HDR 4000. Now this box can take the output from a camera, maybe set up as S-Log3 or HLG with a wide color gamut, put that through this box, and then in this box, we can have a number of outputs, maybe satisfying high definition outputs with standard dynamic range, or Ultra HD outputs with high dynamic range. And we can produce both of these outputs at the same time from this box, a really useful thing to do in live production systems. Now, if you have a look at our website, this website here, you can find all of the products that we are producing in Sony to support high dynamic range workflows in cinematography, live production, and everything else besides. For the switchers, the cameras, you can see here a wide range of cameras, and there's the HDR 4000 that I talked about just a moment ago. You can do the same thing for the cameras themselves, cinematography cameras. We have some shoulder, handheld camcorders, and for the monitors themselves, there's a wide range of different monitors to satisfy every production need. So in summary, producing in high dynamic range provides benefits both for today and for the future. Remember, the ability to archive material can satisfy needs for the future. Modern cameras can capture a very high dynamic range, and there are a variety of industry standards that exist for production and delivery to allow us to get all of that lovely high dynamic range material out into people's homes and into the cinemas. Sony have an unrivaled line of HDR tools and workflows to allow you to build production systems in almost any environment. Okay, if you want more information, please tell us in our survey. We do have a number of other webinars. This is only the basics one, but we do have webinars on instant HDR, on live production using high dynamic range, and you can also visit our website and you can give us some feedback there. So thanks for watching. Let's now open the forum for any questions. Gisbert, are you there? Do we have any interesting questions from people?
Well, yes, we have one question here, but I have to The first one is, will this webinar be available after the live show? And yes, we will make it available via the
Yes,
YouTube channel, I
definitely.
think. So you will get a link where you can have a look at this seminar afterwards. And oh, there are coming questions in. How does log come into play in the post-production process?
What was
How
that?
does that work?
Log?
How
Is
does
this
log?
S-log?
S-log, I think.
Ah, yes, yes. Well, as you know, S-log is a Sony specific curve. It has been very popular in broadcast cinematography live production as a way of transmitting high dynamic range in a standard video signal, but it is Sony specific. But there are plenty of ways of transferring from S-log into one of the industry standards like HLG or PQ. And there are boxes like the HDR C4000 and a lot of editors and graders that will allow us to transmit using S-log as a source material.
Okay,
What
the
other
next,
questions have we got?
another question. In your recently published SR Live white paper, you refer to
Yes,
HLG Live, HLG Natural, and
yes.
HLG Mild. Can you explain the differences between these HLG versions?
Well, there will be another seminar on this subject, which will explain it in a lot more detail. But essentially speaking, it allows live broadcasters to tune the output depending on what kind of input they've got. Just to give you an example scenario, let's imagine that we are producing a program where we're using a mixture of source material coming from high dynamic range, ultra HD cameras, for instance, and we want to blend into it some archive material coming from standard dynamic range, high definition material. Well, the tools that we have allow you to build a workflow that allows you to cater for these quite demanding circumstances. But there is another seminar coming up, and I'm sure the guys from Sony will be able to tell you when this seminar is. I'm not sure what the date is for this seminar, but that's basically what we're doing. It's all about artistic intent, providing a look, and allowing us to get the highest quality output by kind of blending different material together. So that's what all of these different curves, these different transfer functions are all about.
Yeah, and maybe I can add that S-Log3 and 709 gamma curves, they are pretty much in parallel, especially in the lower range of the nits, let's say up to 60, 70, 80 nits. And that allows you, if you use S-Log3 in HDR, to put iris setting even though you only have an SDR monitor, because you will have the same level of exposure for skin tone, for instance.
That's important.
If you would now use an HLG gamma curve, HLG is much lower in this lower range of the gamma curve. So you would set your iris according to the SDR monitor, and then your HLG material footage would look too dark. And HLG Live just compensates for this decrease in the lower end of the gamma curve. So with HLG Live, you can work in an SDR HDR parallel workflow as if you would use S-Log3. So it's just a kind of help. No.
Wonderful.
I just see here the next session is September 30th.
Oh, is it? Excellent. Yeah. Oh, thanks for that.
So that means today in 1 week, next Wednesday, we will have the follow-up session.
So anybody who's interested in this kind of live production, please, log into Sony, get yourself onto that particular seminar.
And there was another interesting question. S-Log, especially S-Log3 in 8-bit, is it a good idea?
No.
I don't think so, because
no, I don't think so. Really, 8-bit video, when you do the mathematics, you go down into the lowlights, there aren't an awful lot of bits left. So no, I think S-Log really 10 bits and beyond.
Also, S-Log2 compared to S-Log3, I think it is the same. You need a 10-bit system.
Any of the S-Logs, it's better to have 10 bits rather than 8 bits. 8 bits is not really enough for any high dynamic range, any Ultra HD work at all, because it's not just the dynamic range, it's also the color. And when you consider how large the 2020 color space is, you really do need those extra bits to give you the resolving power, the resolution, the smooth color.
That is really true.
Yeah.
Another question just came up. Is S-Log3 going to be implemented in all future Sony cameras? I think yes. No?
I would say so. It's quite popular in the broadcast area. You just got to remember that it's not an industry standard as such. It's not specified in a lot of the standards, but it is such a good curve that an awful lot of people are using it as the entry to their workflow. Even though you can't transmit out in the home, it's a really good curve to use as an input, for instance, to an HDR C4000 coming out of the camera.
Yeah. Then shooting HLG, what should I set my zebra for in terms of peak white and 18% gray?
Wow, that's a big question.
That is when HLG line comes into play.
Yeah,
then
I think so. Yes.
Same way as in SDR, so it's the same settings as in SDR, but in HLG you are usually 1 f-stop too dark in the lower part. So
yeah,
I would say that you increase the zebra level, so set it to a higher value.
Yeah, I would say so. But be particularly careful of skin tones. A lot of these extended dynamic range curves, if you're not careful, the skin tones can go into the flat part of the curve. So you do have to be careful that you don't push the skin tones too high.
Too high,
yes.
Yeah. And I also got here an answer from my Japanese colleague about SDR, HDR parallel operation. Both S-Log3 or S-Log3 source materials have to be graded at the later post-process, so that 10-bit recording is much recommended. So that is just he underlines and what you said before. 10-bit is necessary in order to have a good HDR picture.
Yeah. Wonderful. We are running out of time.
Yeah, we are at the end.
Yeah,
the last question was whether the webinar has been recorded, but that is what we already answered before. Yes, it has. And it will, the attendants will get a message when it will, where it will be available. I think on YouTube, but not available for everyone. It will be just for the attendees, I guess, right? Yeah.
Yeah. Okay. I think we're there. Thank you, everyone, for attending. Gisbert was certainly looking at the attendees coming through. I was concentrating on the presentation, so I didn't really watch it. But thank you from the two of us for everybody attending. And I think we will formally close this session.
Yeah.
Thank you.
Okay. Yeah. Thank you very much. And also, I see here a lot of comments. Thank you very much. Very interesting. So you are very welcome. That is the reason why we did it.
Yeah,
and
absolutely.
We are happy to